I was about to say something really nice, that it's so nice teaching my own class because people know how to respond to that. Because I taught Ms. Katum's class this morning, and I did this and like a third of the people raised their hand. But at least you know to be quiet and to come back together, so I appreciate that. It was fun teaching another class this morning, but I very much enjoy teaching this group. So today's class is hopefully going to be very helpful when it comes to your lab. Conceptually, wrapping your head around what are these things that we're working with acids and bases, calculating pH, this kind of stuff. I know some of you have already started working on that, but it is a 2-week lab, correct? Or it'll be the end of the lab. Okay, it'll help you wrap it up. So let's start out with some general concepts, thinking about acids and bases. So go ahead and answer this first clicker question, if you have not already. And check with the person next to you. There's not 100% agreement in this classroom. Find someone who disagrees. Try to figure out why. You agree? Say why? Okay. We had people change their minds and go to a bigger distribution of answers. So would someone like to state their answer and justify it for this evening? And let's go with one person, one answer tonight. So we hear from lots of voices because there's lots of questions tonight. So who wants to start us off? Which one would you choose to put your hand in and why?
Me.
Shelby? Why would you put your hand in acetic acid or vinegar and not 1 molar HCl?
Because hydrochloric acid can burn your hand, and vinegar's
Okay.
That's why.
So just logically in our everyday lives, we hear that 1 molar HCl is, where would you find HCl? Stomach acid, and in the lab, yeah. So our stomach acid is HCl, and we know that it can exist without burning things like our stomach lining, although it kind of reproduces itself all the time. Vinegar, we're like, oh yeah, it's super mellow, right? We could pour vinegar on ourselves and we'd be fine. That's not completely true. The vinegar that we have in the store is maybe like a 0.1 molar solution. And so it is much more dilute than what we would have if we had a 1 molar solution. Don, you want to add something to it? You're just holding your hand out? No, it's all good. You can hold your hand out. Okay, so they are, in this case, not equally as bad. I would still much, much, much rather put my hand in 1 molar acetic acid than I would HCl. I mean, maybe you want to burn your skin off, and then you would answer this question differently. But if you don't want to burn your skin off, you would put it in acetic acid. So let's talk about why. Both of these are acids, right? We're working with acids in lab. Acetic acid is one of the ones you're working with. It really comes down to this idea of a chemical reaction. This far in the semester, we've actually been lying to you the whole time. Believe it? So every single reaction that we've written has one of these arrows. That arrow implies that every one of those things on the left side, in this case, ends up on the right side after the reaction's done. 100% of it. And for this one, it's actually true. If we put HCl gas into water, every one of those HCl molecules will dissociate into a chloride ion and an H+ ion. True statement. But this one is not true. A lot of our chemical reactions will go through the reaction. So this one has acetate. Hopefully you all recognize acetate. And an H+ ion together in a molecule. They can dissociate. But the part that we're hiding from all these reactions and haven't been talking about is that there's actually a reaction that goes in the opposite direction as well. That those products can go and do the reverse of what they did to go through the reaction. So in this case, the way I've drawn it here, these two combine and reform this. In this type of reaction, acetic acid, actually, you'll find if you have 100 of these molecules, you'll have 80 to 95 of them that are still together. and only 5 to 20 of them will be over here. So when I say we have 1 molar of both of these compounds, that means we put 1 molar in water of each of the things on the left side. But that doesn't mean that the concentration of H plus is the same on both sides. Which one of these is going to have a higher concentration of H pluses on the right side of the equation? Why did you say this one, Lena?
Because 100% is this association.
Which means?
That it's 100% gonna come apart from each other.
So if you have a 1 molar solution, it means that if we have 1 liter, we have a mole of H plus ions. We don't have any HCl, we only have H plus and Cl minus. However, if we have a 1 liter 1 molar solution of acetic acid, we have a mole of this to start with, and afterwards we still have 0.9 moles of this, and only 0.1 moles of this. H plus is our definition of acid. When there's H plus around, that's what breaks things down. That's what will tear your skin up, that's what helps us digest food. H plus ions are acid. So the more H plus ions there are, the more damaging it is. And so the one that's on top, HCl, is going to be much more damaging because the concentration of H plus ions is much higher. How do we talk about the concentration of H plus ions? Is there a scale we use to talk about that? pH is the negative log of the concentration of H plus ions in molarity. So we'll get to that a little bit later in class, and we'll spend some time doing some calculations. So that arrow should really be replaced by one of these equilibrium arrows. It means that the reaction goes both ways, and there's actually a lot of reactions that do this. So when you don't get 100% yield for your reaction, now we have another variable for why you might not have 100% yield. Maybe the reaction actually goes in reverse a little bit. Not all of the product is formed. So let's see if we're on the same page. I'll give you 45 seconds to answer question 2 with one of these 4 responses. Once you've submitted your response, check with your neighbor. Couple more seconds. You want to try?
I'm going to try.
Okay. All right. Tara's volunteered to share her thought process for how to answer this question.
Well, I think D. Did you have to have 2 hydrogen for 1?
So what is the ratio in this case of hydrogens to chlorides?
1, so should have been C.
So for every 1 HCl that dissolves, we get 1 H plus ion. That ratio holds true no matter what unit we're using. If we have a mole of HCl, we're going to get a whole mole of H plus ions. So C would be the most appropriate answer for that. Let me take this question and tweak it a little bit. So I'm going to ask the same question again, but this time, instead of HCl, I want you to answer if we're talking about acetic acid. So I've modified the question a little bit on the screen. You won't see that on your clicker screen. But I'm asking this question, if we instead said if we put a mole of acetic acid into water, dissolve it, how many H plus ions are released from that? Okay, we have a bit of a split in the class, significant split. Find someone around you who has a different answer. Ask around until you find a different answer, and then try to convince them you're right.
Yeah, it looks like it.
All right, can I hear from someone in the back corner there? Maddie, Caitlin, Brennan. Why? So for every 1 mole of these that we put into water, 5 to 20% of them are going to dissociate, which means that we don't have a whole mole. I agree. So this is the definition of a strong acid and a weak acid. Strong acid disassociates completely, and every acidic proton is released into water completely. A weak acid, a smaller percentage of it, not 100%. What do we usually see in a molecule? What group of atoms do you notice in acetic acid that might give you a hint that there's a weak acid, that a molecule has a weak acid? So this is a weak acid. If we saw a random molecule, and I said, tell me if this is a weak acid or not, what might you be looking for that would tell you if it's a weak acid or not? Talk to the people around you. Try to come up with an answer you feel confident in. Did you want to answer this conversation? Or? Two things. One is how much it dissociates, and the second is what the concentration of the parent compound is. All right, can I hear from the back kind of corner of the room, back quadrant? What might we be looking for in a molecule that would tell us it could be a weak acid? Help me out. Okay, we'll open it up to more of the class. Cassandra, would you like to?
No, I was sitting here trying to figure.
Okay, Savassier, is that you volunteering? Mel?
Well, if it dissociates, it will still stay together.
Okay, so we know that anything that is a weak acid is going to dissociate some, but it comes back together. Great. What arrangement of atoms in the molecule do that frequently? What part of this molecule? So this part of the molecule over here ended up as CO2 minus, COO minus, started out with that H. Anytime you see a COOH, which if we draw out that molecule, anytime it looks like this, connected to anything, I'm going to say the rest of the molecule is over here. Anytime we see this group of atoms together, instantly we know that this is a weak acid. That's actually, I think, on the back of the...
So here is weak.
So question number 14 is what we just talked about. So then let's talk about strong acids. If you flip back over to question number, well, between 2 and 3, I have this list here. On the exam, I will tell you, here is the list of 6 strong acids. Whenever you see these, we know it has 100% dissociation. Whenever we see a metal in group 1 with a hydroxide, sodium hydroxide, lithium hydroxide, potassium hydroxide. We know those are all considered strong bases. And sometimes group 2 metals attach to hydroxides, but a lot of times they just don't dissolve, so we don't consider them a strong base. So go ahead and fill in the formula for all 6 of these acids. Hopefully you know some of them. Maybe I'll start us off with the first one. I'm going to be very generous. I'm going to give you the first one. How's that for generous? You're welcome. Go ahead and fill in the rest of them as much as you can. I'm going to give you 1 minute. Try to think about your polyatomic ions. The top half is not polyatomic ions. The bottom half is. They have polyatomic ions in them.
Yeah.
Good start. No, I mean, I'm serious about that. A lot of people forget that part.
Oh, I do know. Just like a damn top cell.
We're supposed to do this.
Okay,
Put an H in front of it.
that's about a minute, right? Can I have volunteers to read off
I'll do the first one.
second one?
I'll do the
Go ahead.
second one.
HBr.
All right. Hydrobromic acid, HBr. John Paul?
HI for hydroiodic acid.
Hydroiodic acid. Great.
Oh, that's it.
Nitric, Alexis. HNO3. It throws you off a little bit because you think it might be nitrite, but it's actually nitrate. NO3 minus with an H plus. So think about when each one of these dissolves, it's going to give off a proton and whatever that anion is that was attached to it. Right? These are all strong. It means 100% of it goes to that side. Sulfuric acid. Who wants to give that? Shelby? I think this is your second one for today, but H2SO4. So if this one is involved in an acid-base reaction, how many H pluses are we going to get? 2 H plus sulfate. 2 minus. I was going to call in Olivia for this one, but Chad, what do you have for perchloric acid?
HClO4.
How did you know that one?
Perchlorate or ClO4.
So perchlorate, but yes. ClO4 negative is perchlorate. This is perchloric acid because it's attached to an H plus ion. Dave?
Will you give us the formula on the exam or just the name?
That's a good question. I think I'll give you a list of names because you know all of these 3 polyatomic ions. You know them.
Yeah. I'll die.
Perchlorate? Okay, well, I'll make sure that's on the next exam.
I got confused.
All needs a little extra time on that exam. That's all we need. We're
I
trying
think
to
that
slow
nitric
people.
acid is going to be HNO3 and not just
We get more time on
HN.
the final.
Get my question.
That'd be nitride. And I don't know that forms an acid. I don't know. This is nitric acid. It's one of the ones that we know and we use frequently.
So am I right?
Yeah. It's hard to think back to when I didn't know it to put it in context for... Does that make sense? Sorry. Not very useful answer.
He just knows it so well. It's just.
So if we're talking... This is what happens when a strong acid goes in water. Every one nitric acid generates one H plus ion. So if we think about a strong base, what's going to happen when KOH dissolves in water? Strong, so we're going to get a K plus and one OH. What about, I'm going to do one more. I'm going to do it up at the top though. What about this one. Calcium hydroxide. What happens when that goes into water?
Hydrogen and calcium oxide.
Cut it in half.
It's a strong base. It's a hydroxide with a metal. So what's going to happen?
Calcium trick question.
No.
Hydroxide.
Calcium ion and hydroxide. What charges do I need? What's the charge of calcium? So what's wrong with my formula there, my reaction?
You need 2 hydroxide.
2 hydroxides, 2 hydroxides. So every 1 calcium hydroxide releases 2 hydroxide ions. So when you're thinking about titrations in your lab, I don't think you did any with calcium hydroxide, but you have to pay attention to what the stoichiometry is in your reaction. And good amount of time for, now we can go to learning objectives. What we're doing today is, ready? And this is all recorded. You can always go back to the YouTube video. All right, so I want you today to be able to look at a molecule and say, that's acidic, or that's basic. Either because it's one of the 6 in that list that we just made, or it's a strong base, or it has a CO2H in it, it's a weak acid, or we're going to talk about what a weak base would look like. And then I want you to be able to calculate also the pH of a solution based on the concentration of H plus or OH minus ions. Are you already amazing at this? Calculating the pH or pOH? We got that. All right, so this should be a quick class. To put all of this in a little bit of context, you're going to see P a lot in your careers, but in chemistry, you'll see it a lot as well. And whatever the P is in front of, it means take the negative log of this. So the examples that you've seen a lot so far are pH. What does that H stand for? Hydrogen ions. So this really means take the negative log of the H plus ion concentration. Is it percent mass, percent volume, percent weight? What kind of concentration of H plus ions are we talking about? Molarity. So if we know the H plus ion concentration, we can find the pH. What does pOH mean then? Concentration of OH minus. So the concentration of hydroxide ions, what is a negative log of that? How do you feel about logs? You super comfortable with logs?
Are you going to ask us to calculate? Do I need to get a calculator? What you're saying is the molarity that's in those brackets.
What's the negative log? Let's do something simpler. Let's do, what's the negative log of the number I have on the screen? Ask your neighbor, what's the negative log of that number? Discuss it with your neighbor. Try to come up with an answer. If you need to, you can use a calculator. Try to guess. Okay, so what's the negative log of this number?
3.
Why is it 3? What does a negative log mean? It's the negative of this exponent. So what is the P? If we say the pH is 2, what does that mean? It means it's acidic. What's the concentration of H plus ions? So H plus ion concentration. We do square brackets to say molarity or concentration of a molarity. It's kind of a shortcut. 1 times 10 to the negative 2. So what the pH scale, this negative log scale, does is how big or small is the exponent of the concentration? Is it super, 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 super small? In which case you have a big pH value. Or if you have a really small pH value, it means that you have 10 to a relatively small exponent, which means it's a pretty big concentration. So logs are always really difficult to kind of wrap your head around. It's what is the order of magnitude, kind of like earthquakes, right? So if you haven't, we grew up with earthquakes in Arkansas?
No.
I mean, in northern Arkansas, there was a whole bunch of earthquakes in like the 80s, right? Yeah, there's a whole bunch up there for a while. Anyway, an earthquake can either be like magnitude 1, 2, 3, 4, but every time you go up a number, 4 to 5 is 10 times bigger of an earthquake. 5 to 6 is 10 times bigger of an earthquake. So it's exponential every time with the power of 10. So pH is kind of the same thing. I don't know if that helps at all. So I want you to have a little bit of context. So if you have an acidic solution, you're going to have a higher concentration than if you had, let's say, if the pH equals 5. Then your concentration of H plus ions is going to be 1 times 10 to the negative 5th molar, which is much more dilute, less acidic, lower concentration. More acidic, higher concentration. Seeing a little bit of the trend?
Because, yeah, that's it. The bigger the bigger the smaller.
Exactly.
Smaller.
So let's go ahead and do some calculations. I want you to answer question 4, and then see if you can answer question 5. So work through questions 4. If you can't do 5, you can skip it for now. Then work on 6 and think about 7, and we'll talk about how they tie together in a second. Go ahead and click in your answer to the question.
No, we're going to do question 3.
Oh, sorry, we're on question 3. Question 3.
Yeah.
First answer is right. Well, first answer I got.
I was expecting to do
Is it, do you think it's pretty acidic?
yeah.
0.75 molar?
But if it, I thought I was
But
going
if
to
you
like a straight number.
2, how would you say? Okay, because on the master thing, me and Ed, like, got fight on that thing.
Probably safe to
Yes, and I was so pissed. Because I could have got it in the first answer, but it
Can you do
was
us a favor, when you're doing these problems, can you write out what you're calculating? So as we come around, we can get some idea of how you're calculating it, please? Go ahead and put a 0 on your decimal, that way they don't get lost, especially if I just see 125 and I'm like,
Can you do this next one the same way? You know, the next one's different.
That's what I was wondering, like, how do you, like, what?
you write out. Start bringing my pressure We have 25 responses. Make sure you hit submit after you type in your answer for question number 3, please.
Sin, it should say sin.
Or 31. Okay, let's let's write this one out. I don't know if this is a great one to have student input on because it's just we're using the equation that we talked about. So remember, P means the negative log of. H is referring to H plus ion concentration. So you want negative log of the H plus ion concentration, 0.75 molar, equals 0. What's the next number? 49 or something?
My face went to 3.
I'm wrong. pH of the solution is 0.12.
Not 3? Oh, crap.
You only round one past the decimal or the digit. You guys are gonna hate sig figs when it comes to pH. I will tell you that on my exams I will not grade harshly on that. We will not grade harshly on that because it is not intuitive, but it kind of makes sense. Okay, so does this number seem reasonable?
Yeah.
It's no.
Put it in scientific division.
So what are we referring to say is this number reasonable? What is a reference point?
The number of H plus ions.
Hydrogen is
What is the scale of pH and where should this be on the scale?
Super acidic.
Okay, it's probably going to be pretty dang acidic because pH is neutral when it's 7, and we have a good amount of just this ion itself, which is the definition of acid. So it's going to be pretty acidic. So we expect it to be low. Can we ever have a pH value less than 0?
No.
Yes.
What happens then?
You can. So the thing that a lot of people remember, which is what we need for the next problem, is that our concentration of OH minus is very closely related to the concentration of H plus. As one gets bigger, the other gets smaller. What comes out of that is this. You know what this equals? So if we know the concentration of H plus ions is very high, small pH, we have a very large POH, small concentration of OH minus, right? As one of them is lower, the other is higher, which means the concentrations are the opposite. So a lot of people say you can't have a pH value less than 0 or greater than 14 because they're like, but then what do? Negative numbers are fine. So does anyone want to tell me what is the pH of a 1.25 molar solution of H plus ions? Can you calculate that?
Negative 9.7.
Negative what?
I got -9.7.
Negative 0.9.
Oh, it's inside.
Yeah.
0.096.
0.96. Okay? If we have greater than a 1 molar concentration of H plus ions, we're going to have less than a pH of 0. So just know that can happen. You can also have a pH greater than 14. It means there is so little H plus ions, we really couldn't even measure it. It'd be ridiculous. Okay. So now can you go ahead and answer the next question? What is the pOH of this solution that we're working with? So question number 4 now, is that what it is?
She doesn't want us to know that we know she knows.
She's over here on
That's what we stay with low.
I got 13.75.
So we have to do. We have to negative this to there, subtract something.
All right, make sure to submit your responses, please. All right, can I have a volunteer to tell me how we did this, Courtney? So I'm going to rearrange equations to do what you said. So if we know the pH, if we know either one of these, we can find the other, because we know they have to add up to 14. In this case, we know the pH, so we're going to isolate the pOH. And so we did 14 minus 0.1249. Use as many digits as you have in your calculator. And then after you do that, then you can round your answer. So what do we get? 13.88. All right, here's where you're going to hate sig figs if you haven't already figured this out in lab. When you're describing a number that has a logarithmic function to get to it, we did POH. This is a logarithmic value. It's on that logarithmic scale. The number of digits past the decimal are significant. Only those. So whatever's here is here. Leave it alone. It's 13, it's 12, it's 10. Because remember what I said a minute ago, that this digit here tells you the concentration of OH minus is 10 to the negative 13. This tells you how big or small the number is, the concentration is. These, how many digits we have here, tells you how much precision we had in that measurement. So, how many significant figures is the value that I wrote out here? 2. It's only 2 significant digits. We show that because we put 2 past the decimal. And then the 13 tells us the concentration is 10 to the negative 13 of hydroxide. A little bit off from that, right? But it's in that ballpark. So this tells us how big or small. These ones tell us how much accuracy we have. So you feel like you can do the next couple of questions now? So 13.88 was our answer we wanted. So let's go ahead and find the pOH of the solution of question 5. And then once you have that, write out how you would find the pH of that same solution. Oh, really? It's okay, the next one's open.
So maybe it'd be good to start with pH. Okay.
So which negative log do you have H plus ion concentration? If you do the negative log of that, you find the pH or pH.
This is all wrong.
It's all wrong. Why are these pointing?
I have to plug it in my calculator to figure it out. I just know ballpark, it's around that.
Is this what you're wanting to do, like
So this one?
Oh, no, the answer is 9.53. Yeah, because we found the pH. Because we're calculating from the OH concentration, so all we need to do is just the negative log. But in order to find the
All right, we only have about half the class responded. Flag one of us down if you're not feeling comfortable with this. How are y'all doing? How did you answer this one?
Well, log of that. I guess I should.
So what is this value?
This is the POH.
There you go. So label that. And then the next steps, I think you were answering the next question. Great. So hard to use one of these and do logarithms.
Yeah.
If you have the H plus ion concentration, yeah. Do you? pH is negative log of the H plus ion concentration. Do you know what the H plus ion concentration is? Yep. All right. Robert, would you be willing to share how you answered the first part of this question, or the first question?
I took the negative log of the POH.
So I'm going to change your wording just a little bit. We're finding the POH, so POH equals, so we're taking the negative log of the concentration of OH minus, which is that number you're talking about. Is that okay to change that a little bit? 0.269 molar. And what did you find numerically from that? So I'm going to guess that when you put this in your calculator, you might have missed that negative symbol. Because the POH for this should probably not be a negative. It can be a negative. It's allowable. But in this case, because it's not greater than a 1 molar, if this was 1 molar or greater of hydroxide, then we expect it to be negative. So that's the kind of check we can do. It's really hard to do on your phone. I agree. Okay, so Robert found the POH. How many digits should we have for this number? Should be 3 significant figures, right? Because this one is not logarithmic. 1, 2, 3 sig figs. So is this correct?
No.
What should I do? How many digits do I take off? Is it 1.57, 1.570? 3 past the decimal, 3 significant figures.
Oh, okay.
Yeah, Jay?
I have a question. So, you know, the first example we did with the pH of 0.75, we found that answer for the pH with negative log.
Correct.
Why is it the same as finding the pH for this one?
So remember we had the P, it's the eraser. P means take the negative log of the concentration of something. If it's pH, then that's H plus ions. If it's POH, that's OH minus ions.
You do that for any other ions?
You can do that for other things in chemistry. So we have this thing called pKa. We have pKsP. We have a whole bunch of different P things, and it's always take the negative log of it. Alexis? So, Monica, can you discuss kind of what we talked about right at the end there? With why we don't... I think you were saying, why don't we just take...
Because I didn't know the H plus.
Okay, so a lot of people are like, can't we just take the negative log and then that's the H plus ion concentration? But remember, it's P of the negative OH minus concentration, so this is, by definition, the POH. We don't have the H plus ion concentration. We can't find pH. There is a way that I think you have learned in your lab that you can find the H plus ion concentration. Is that what you're referring to? No? Yes?
No, I was just confused because we're not looking. You don't look at pH first and then find that.
How would we find the pH first?
Negative log.
Of?
0.0269.
So we can't take the negative log of this and call it pH. because this is OH minus concentration. So P, the negative log of this concentration, is by definition POH. Does that sit well?
Nope.
So if I had the H plus ion concentration, I couldn't take the negative log and call that POH. So I have to do negative log of whatever that thing is. If it's this, I can call that pH. We don't have this. So I think there are mathematical ways you can find the H plus ion concentration if you have the OH minus ion concentration. For our class, on our class exams, unless we do it next Monday, I'm not having you convert between OH minus and H plus ion concentration. If I change that, it'll be a Monday in class, and we'll go through and practice that.
So we won't have to learn that.
So for right now, pause.
But that's all
We need to be able to say, come on, Kier, help me out. If we take the negative log of something, and that something is OH minus concentration, we have to call that POH. If this is H plus ions, we have to call that pH. So it's either POH or pH, one or the other. If we have one, how do we find the other one? If I want pH now, I can't use this equation because I don't have H plus ion concentration. So how do I find the pH?
Our little algebra one.
14 minus POH is our pH.
That's right.
So what would our pH be for this exact example here? 430.
Why are you adding the 0 in there?
Because this is 3 significant figures before we made it a logarithmic value, so we have to include 3 digits past the decimal. Okay. So that is actually the answer to the next question. We just wrote that out. So if you notice, as the pH gets higher, POH is lower for that solution. If we look at another solution, if they're both close to, if one's close to 7, the other's going to be close to 7 as well. So if you ever do some math and you come out with those two numbers not being opposites of each other around 7, we know we did something wrong. Carmen, do you have a question?
You answered it.
Fantastic. All right. Let's take this up a notch. Question number 7. What is the pH of a 1.25 molar HBr solution? And here's what's going to be the hard part. I want you to write down exactly what you're plugging into your calculator. I need to see this as I walk around. So please write it down on your piece of paper.
I don't take notes just for the note cards. They're all fun. I just like taking notes in color because it's the more pictures.
Because this is just, no, like,
Okay, we have 20 responses. Submit, submit, submit. Okay. So here's a little bit of a tricky problem. Did anyone find what the problem was? It was what?
Negative.
Okay, so let me expand maybe on what you're saying. Okay, we got a molarity. We're going to do negative log 1.25 equals negative 0.9. 0.909. All right, great. So, Crystal, what did I mess up on?
If you're just looking at it, you just took the pH of 1.25 molar when you're actually looking for, if you're just looking at it, you took the pH of the hydrogen ions when you're actually supposed to be, and when the solution was, the molarity is for the entire solution of H2O. I mean,
So with the thought process that I said out loud, did I take the pH? What did I take? I took the pHBr.
Yeah.
Not the same thing.
That's what I said.
Let's, in this case, numerically, it's going to turn out the same.
Because there's one hydrogen.
Because every HBr, strong acid, disassociates fully into one H plus and one Br minus. So the concentration of H plus ions in the solution happens to be 1.25 molar. So this equation ends up being okay, but if it was anything other than a 1-to-1 ratio, we can't just take the negative log of any number that we see and call it pH. It doesn't work like that. Because it's not H plus ions. We'd have to call it P of something else.
No one would know.
It's too much P today. It's a bit rough. Okay, so if we had H2SO4, would we be able to say the concentration of H2SO4 is the concentration of H plus ions?
No, but we cut it in half with that.
Because every one of these, kind of sort of, releases 2 H plus ions. So there is a stoichiometric ratio you would need to think about.
Or could you do the negative log twice and add them together?
Nope.
Could you do one?
Logs do not add together. They are very unfriendly with addition, I'll tell you that. They are rough. Okay, so let's keep that in mind, that we can only take the negative log of H plus ions or OH minus ion concentrations to find pH or pOH. You cannot do it of anything else, so you always have to think in terms of H plus ions or OH minus ions. And I think I have this all written out. Oh.
Almost. That was almost it.
All right. Let's go ahead and answer question number 8.
Well, I'm gonna ask you something.
No, I agree with you.
Well, first, I like come up with and then I converted them.
I got 91%.
Here we are, making worse. I'm right, you're If you want sushi, go to sushi. No, never get Kroger sushi. Go to Soul City. Go to Soul City. 50% off sushi all the time. This is important information. Soul City on Westmont. I will literally get California roll is literally I'm not kidding.
Is that 15 responses?
No, that's Soul City. 50% off sushi every
More specifically?
You didn't even have to raise your hand.
Raise your hand if you need 30 more seconds. Would that be helpful? 30 more? Okay, go ahead and take 30 more seconds.
No.
Why do you?
Why did you jump?
Weren't you raised here?
From Seattle. I was born here. My mother's from there, so I spent 3 years there. Okay, this is kind of bringing together a few things we've been talking about so far. So I would really emphasize that if you're struggling with this question, with how to put together a whole bunch of conversion factors, this would be a perfect opportunity to be like, let me stop by office hours or come by at one point, because this would be really helpful for all the rest of the stuff that we're doing. So let's go ahead and, do I have a volunteer who feels pretty comfortable walking through this? Jay.
She's got it.
Unpack the what? Okay, so we'll come back to you for the calculations. Who wants to help me with what I'm getting at here? Alexis? So what is on the top? Right, so if we have 1.25 m, what does that mean?
Over 1 liter.
Moles of what? Per every 1 of solution. Okay, go ahead, Jay. So we need to identify our conversion factors so that we can do all the calculations starting with our initial quantity. Fired. Okay, so just tell me what you converted with and to, and I'll put it into the format that I'd like you to do it in.
Okay, so I just put it over 1,000 liters, and
One-
then I got
1,000 what?
1,000 liters is a liter. I mean milliliters.
Okay,
Yeah, 1 liter is a milliliter.
so we convert from milliliters to liters, and then what?
Yes, and then I got. This I said I didn't do what you said to do, because then I got 0.00625.
Nope, that's why we don't stop.
Okay, so
So I'm going to put you on freeze for not doing it my way. And I'm going to ask for someone who did dimensional analysis to walk us through the next couple steps. Dustin?
The next step I did was I multiplied that by 1.25 moles of HBr over 1 liter of solution.
Okay, and I'm just going to kind of backtrack to say why. So we did milliliters to liters. We did liters of HBr to moles of HBr. And then go ahead.
And then I didn't do sig fig so I could plug it into the logarithm. The logarithm? Nope, that's not right.
Yeah.
To the thing. And so my answer was 0.0090625.
Okay.
That's what I put in the parentheses for my negative.
So we're still missing one crucial step. Alexis, you want to add to it? Okay, so then we're missing 2 crucial steps. Sam?
Is it times 1 mole of H plus over 1 mole of HBr?
Remember, this question is about how many H plus ions there are, not how many HBr compounds there are.
Oh, no.
Okay, and then, Sam, can you finish it?
And then 1,000 millimoles of H plus over 1 mole.
And then what did you find for your numeric value?
9.06 millimoles of H plus.
Does that sound right?
Yes.
Okay, typo.
Milli means 10 to the negative third. It doesn't matter if it's liters, moles, grams, milligrams, right?
It's a
You've
mole.
had typos before, so I see where.
Yep, but you will very frequently see millimoles. Tay, you have a question?
I'm confused about the sig figs.
So sig figs in this one, we have 3 sig figs here, 3 sig figs here. We did not take the logarithm of anything, and so it's 3 sig figs here.
So, if you were to have taken the logarithm, you would have to do sig figs after you
You would have to do 3 decimals past the 3 digits past the decimal. Correct. Okay, so this problem kind of exemplifies how we need to be really specific. Why do we have to do this step right here? Why do we need to convert from milliliters to liters?
molarity liters.
The molarity is in liters. Why did we do this step? We went from how much volume it takes up to how many moles are in that volume. And then we said, well, for every HBr, we know that we form one H plus ion. And then I asked for it in millimoles. So it's a lot of different steps. And I would argue, Jay, that if you did this as 4 or 5 different steps, that you're going to lose track of what you have and what the units are, and it's going to be much more difficult to see where you might have gone off track. And I can tell you as a grader, it is extremely difficult for me to follow that. And I have much more of a tendency to give partial credit if you mess up a conversion factor versus if you do all the calculations separate and you mess up because then I can't follow it. All right. The next part of our little worksheet here is kind of some terminology. So I keep saying H plus ions. It's tiring. I just want to say proton. Is that easier? Is that okay?
Wait, proton, why? Wait, do you have to? Is this like a chemistry thing?
So if you have a hydrogen ion, what's it composed of?
One proton, one
proton.
One proton, one electron, because it's neutral. What happens if I make it positively charged?
It's just a proton.
It's only a proton. So an H plus ion is, by definition, only a proton, and so shorthand chemists refer to H plus as proton. Where does the proton transfer? From here to here. That means that all of the definitions we're using, if you've been reading the book, you'll find Bronsted-Lowry is one of the types of definitions of acids and bases. So something that is able to give up or donate a proton, an H plus ion, we consider that an acid. So if you look from the left side of a reaction to the right side, if it gives up an H plus ion, it has to be the plus, then that's the acid. If it's something that takes that H plus, that's what we call the base. That's an acceptor. How do we define strong and weak? Right, the next two on your questions 12 and 13, strong, weak. How do we define those? Go ahead and write out your thoughts really quick. What is strong, what is weak? What are we focusing on for strong and weak?
Dissociation.
Focusing on dissociation.
Why is there a dash between the O and Bronsted?
Because it's Danish. Brunstad, something like that. I don't know. Something like put a potato down your throat and try to say it. That's what that O with the slash means. Okay, so strong means that we have complete disassociation. Weak means it's partial disassociation. And then remember I said that if you see a molecule and it has a COOH or a CO2H or the carboxylic acid the way I drew it out earlier, that means that it's a weak acid. And then I'm going to add something so John Paul takes another picture. And there's a telltale for it being a weak base. And that's anytime you see a molecule that has a nitrogen in it. But it's not just any old nitrogen. What does that nitrogen have to have? Has to have a lone pair on it. And then other things attached. I simplify this. But if it has a nitrogen and a lone pair, then that is, by definition, a weak base. It can accept an H plus ion. Okay, so let's see how we do with identifying.
What do you mean? How do you know? Like if you wrote a formula out with that nitrogen.
So I'm going to send out this clicker question, and then I can go back for a second. So I want you to look at the 3 molecules that you have. On your phone, it should show which one is which. And then, Tony, this... I'll give you a couple seconds, and then let me know when we're ready so I can flip it. You good? Oh, sorry.
It keeps disconnecting me.
Go ahead and select which one you think is a weak acid. Check with your neighbor.
I went with B.
Okay, a couple more seconds. Who wants to circle why they chose their answer? Someone who hasn't talked today. Anyone? Julia.
Do I have to explain?
Yep. So Julia's going to explain and she's going to circle. Be more specific.
Oh, circle Y?
Yeah, circle Y.
Circle what in there? Oh. Wait, how do I go back? It's these two. This. Wait, I know it's
Here, I'll give you a
COOH, but I don't know
different-
the exact please. Guys, I'm fixing it, don't worry.
I'll give you purple. Go ahead.
Okay.
Last try. Three.
I know it's this.
Two.
Okay.
1.
Go back to it?
Okay, there we go. Okay, so remember, we're looking out for any time we see a CO2H. That's going to tell us it's a weak acid. And if we're clearing all this off so we can actually see what's under there, CO2H. This right here is a functional group. It's a part of a molecule that would always be a weak acid. So we see that and we know by definition it's going to be an acid. Most of you had that. So if we take that molecule, we're running low on time, so I'm going to try to kind of hustle through this. If we take that molecule and we put it in water, we're going to get the dissociation of that H+ that was connected to the carboxylic acid. Which of these arrows is the most appropriate to represent that reaction? Couple more seconds.
Oh my gosh. How am I supposed to get quicker participation?
5 more seconds.
Please, I keep disconnected.
And we're closing out.
There goes my participation.
All right. Why would we choose A? Our definition of a weak, I need everyone together. We only have like a minute and a half or 2 minutes left. And I need to get through all these today because it's going to be super helpful for your homework. If it's by definition weak, it means it is not only going to go to the right. B is wrong. That's what we've lied to you all semester. Reactions don't just go in one direction. It goes in both. And so the way we show that is this arrow A. That's an equilibrium arrow. So let's then take a look at this molecule. 15 seconds.
I just want to connect. Please let me get quicker participation. It's not happening. Life is bad. Grade is bad.
And closing out. All right, so let's talk it through as it's still open so you can submit a response. Can it be a strong base? It would have to be a metal and a hydroxide. Nope. Could it be a strong acid? It's not one of those 6, so it's not a strong acid. Is it a weak acid? Does it have a COOH?
Yes.
Where? COO, but that's not an H. Hopefully we know the difference between carbon and hydrogen, so we're good. So, hopefully you notice that that nitrogen only has 3 things, and that's a weak base. Okay, and this is cocaine. This is the free base of cocaine. This is rock cocaine. Crack. Okay? We're not done yet. So when you hear free base, it's referring to one of those 2 forms of cocaine. Okay, the last thing we're going to do is conjugate acid-base pairs. So the idea is that when something goes into water, if it's an acid, it's going to give up an H+. If it's a base, it'll accept it. So if we look at our options, this is formic acid. The formula is the same. This is the formula, this is the structure. Which one of these is considered the conjugate base of this acid? Wasn't that your homework?
Yeah, it was terrible.
Oh my God. No, probably.
Okay, so here's our chemical reaction for this acting as a weak acid, giving up a proton to water. So the thing that is the conjugate base is on the right side of the formula. When it goes backwards, which of those 2 things acts as a base? Which of those 2 things acts like a base? when you say going from the right side back to the left side? What do y'all think? Go ahead and click on your responses. We have a majority of our responses. So, this is the acid, this is the base, because this one donates a proton, this one accepts. Over here, the reverse reaction, these are called conjugates. On the right side, conjugate refers to, in the reverse reaction, this is a conjugate base, because it acts as a base going that way. This is a conjugate acid, it acts as an acid going that direction. Do you want to do the last two? Sure. Last one? Okay, so closing out. This one. Alright, so I've shown hydrogen phosphate, HPO4 2-. Here's the structure, there's the formula. Which is the conjugate base for this one? Couple more seconds. Gonna go ahead and close it out. Bam!
Yeah, we got that, right?
So if this one loses a proton, that's going to be considered the conjugate base. So it's with an O- here, which is this one. So then the next question, the last question, what is the conjugate acid of hydrogen phosphate? Turns out this can act as both an acid or a base. It can either lose a proton or it can gain a proton. In this case, we're saying it's gaining a proton. What's the conjugate acid? So what am I going to put right here? If this acts as a base, what's the conjugate acid it's going to form? Which is what the majority of the answers were. Alright, so conjugate acid base is all about if we lose or gain one proton, what does it look like? What's the reverse of that reaction? So it's only one proton away, which is why this is wrong, because this would have to be 2 protons gained to get here. Alright, thank you for your time and your patience. I appreciate it. If you have any questions, I'll stick around for a little bit.